Let's start today's session. So last time we discussed about use of very basic algorithms in machine learning, that is 0R and 1R. And we are going to discuss the next one under the topic decision trees. We are going to basically look at what a decision tree is and how we can build decision tree from data. I think we need to understand what decision tree is. Usually it'll be a tree-like structure where you change the orientation from top to bottom, and you will have what we call set of nodes and branches, and at the end you have something called leaves. Remember, this decision tree will create using the data we have. So let me show you an example. So this is the decision tree created for our weather dataset. As you can see, in our weather dataset, we have several attributes. So we have outlook, humidity, and windy. They are the attributes. And the branches will describe each of attribute values. So for example, outlook, we had 3 different values: sunny, overcast, and rainy. And at the end of the branches, you will have something called leaves, which represents the final classification. For example, if outlook is overcast, then we will say, okay, you can play the game. Right. Now, the question that we need to first work on is how a given data set we create a decision tree. So this comes with what we call the divide and conquer approach to create the decision tree, which is also known as top-down induction of decision trees. So there are a few steps we need to follow. We have to start with, first of all, deciding which attribute to place in the top of the tree, which we call root node. For example, our data set, we have 4 attributes, right? We have 4 attributes. So our weather data set, we have outlook, we have temperature, we have humidity, we have windy, and finally, we need to predict the class, which we call the play attribute, which consists of yes and no. Given this data set, we need to create a decision tree that we have seen earlier. The question is how, right? So first of all, you need to decide which attribute you are going to use. So out of the 4 attributes we have, outlook, temperature, humidity, and windy, we need to select one of the attribute to put it as a root node. And once you do that, for each attribute value, we have to create branches. And you repeat this process. How do you end this? If you take instance in the node, if they all have the same classification, we have to stop at that point. That's where we define something called the leaves. And now, how we are generating. So the first step is, okay, you will be given a data set. This is the weather data set that we have discussed so far in the module. And you can notice that there are 5 attributes, including the class attribute. And then you have a set of attribute values. Outlook attribute. And if you look at the outlook attribute, you can have 3 different values. So you can see sunny, overcast, and rainy. So which means we have to have 3 values. So let's start with 3 attributes. We have sunny, we have overcast, and we have rainy. So we have to create 3 branches. So let me put the values. So the first one, let's say sunny, right? And then we have overcast, right? And then we have rainy. Then look at with the attribute value. For example, if you look at sunny, the first value, sunny will be no. The second one will be no. So you can count how many times yes and no appears. So starting from no, how many times? So sunny no, again sunny no, then sunny yes, sunny yes. So there are 3 instances in no, and there are 2 instances with yes. This is the how the values are separated for outlook when the value is sunny. The second one is we have to look for the overcast. Now, given overcast, this one, you can look at what are the values, and one knows. So we can say no will be 0, but we have 4 instances with yes, right? So similar to that, if you look at the rainy, we will have yes and yes, no, rainy again, no. So which means we have 2 instances, no. So 3 yeses. So that should be, it should be like this. Right. Now we get Outlook attribute and we create branches for the 3 different values, that's sunny, overcast, rainy. And we observe its classification, right? And how the data routed down in the tree. So originally we have 14 instances. Now each branch we have again here 5, 4, again 5. So which means we have to further work on the problem. That's what we discussed in previous slide. So you can do this for all the remaining attributes, right? And if you look at this, it would be look like this. If you repeat the same thing I did it for Outlook, this is what you will get for temperature, humidity, and windy. And if I reiterate what we need to do right now, we have to select one attribute out of these 4, and we have to put it in the root node. So my question is, how do you select, right? Out of the 4 attribute, how do you select from the top? So when I ask you like which one we can select as a root node, we can select all the 4 depend on various reasons. So it's perfectly all right if you select Outlook, if you select temperature, humidity, and windy, because you might have different reasons to issue, right? So therefore, you need a justification why you are going to select. For example, there's a machine learning algorithm called random trees where it selects the attribute at random. So any of these 4 attributes could be on top in a random tree. But if you look at in machine learning, we normally prefer to have simple models. So therefore, in tree also, we want to have a very simplified decision tree, a simple decision tree. If you look at in that aspect, you need that we need to stop, right, as soon as possible. So therefore, if you look at all the 4 attributes, only here we can see the same classification, which means we can finish up to this point, right? So that is one advantage you will get. You can identify which branches are simplified. In this particular case, since all the classifications are here, we can say that, okay, we can finalize the overcast with yes. But the other 2, we have to rate, which means we have to look for other attributes. Right. Having said that, if you look at the simple decision trees, you can notice Outlook attribute, everything is classified here as yes, which means we can stop at this point, which we can hope that this will give you the simple decision tree. Similar to that, if you look at sunny attribute, we can notice that 2 yeses and 3 nos, which means we have to select other attributes. So depending on Outlook, let's say we have decided to select that. Then next thing would be you have to repeat the same process we did earlier for different conditions. You have a template, humidity, and windy. So you can see here now, given this one, let's say the first one is A, the second one is B, third one is C. What would be your answer? Which one you are going to process? So how we start earlier is we went through each and every attribute and we looked at what is happening with the class attribute. And no, you have noticed that, for all the 4 attributes. Then the next one is we have to select one of the attributes as a root. You can have various answers because there's no one single answer for this. I told you if you use random trees, you will select one at random. But what our intention is, right, we can have very small trees if you smart. So Outlook, we already selected as a root node. Then we put other 3 attributes, that is temperature, humidity, and windy. Right. Now, going back to the previous one, if you're looking on the same classification, like in this case, right, we can say that in this branch, we can have humidity because it's pure 100% selection for this. So humidity is high normal. This branch is that. Middle branch is also done because we said everything is yes. The third branch that we need to take care of. The remaining two attributes are temperature and windy. You put it there, you get this information, and then you can look for the survival. Right. And finally, we have two other options, but when we put it in windy, windy gives us the the best accuracy in terms of you are selecting attribute type. So having said that, there are a few things that we need to understand and discuss. The first one is which one is the best attribute, which there are ways that we can find out, but at the end of the day, right, you can see or you can argue for one single computer, right? So when we are defining best attribute, we have to ask back, right, what is the requirement? So if you have, again, you will get a small tree, right? So the idea that we want to highlight here is we want to get the attribute and we have to produce the purest nodes, right? That what we have seen earlier is very simple graphical representation, but when you go to calculation, we need some mathematical basis. So in WEKA, for example, they are using information gain, right? So now strategy is like you have to select the attribute, then greatest information gain. So that is what we expect when we talk about the decision trees. Right, now we discuss something called the computing information, right? So that can be done using this is equation for entropy, and the p values are p1, p2, pn probability values. So for example, if you have p1, then the expanded version will be p1 log p1, p2, then p2 log p2. So that means these probabilities we can calculate by going through each of these attributes, and then for that we can apply, we can take different fractions p1, p2, and pn, but then again we can have it, right? So p1 log p1, p2 log p2, and finally minus pn log pn. That's how the formula for calculate the entropy. So what happens in this particular case when you take the starting point? So the value there will be minus p log p, right? So I could be any value. And then sometimes what might happen, they can start with next. So in this particular case, if you calculate the data using send information dj, and then finally you come up with the information info d. And information gain in particular are known as getting this syllabus covered in the first place, and then they will discuss. So this grain A, you can implement like E and info AD. Right. So having said that, the next one is how do you calculate this? I'm not going to go into details, but then again, simply you go through each of attribute values and look at the information, and you provide two values to represent yes and no in the data set. Right. Let's say we get some number if you apply same equations that we have just seen. So outlook, we have to find out the information before the split and different information after the split. So that's what we have written here. We will get the information in the beginning. We have 14 instances, and then they actually routed down to 3 values. In this particular case, when we say info 9,5, so that's for the before the split, and that means you have positive yes 9 classes and then negative classes, and then again we have 3 branches. Each of these branches, this is how the values varies. We set outlook is sunny, overcast, and rainy, and depending on what you selected, you will get these 3 information. So that means you calculate the information before the split and calculate the information after the split. So in this particular case, So if you compare, you will get about 0.247, right? And if you done this, the calculation for the four, this is what we will get. So outlook is 0.247 bits, then temperature 0.029, humidity 0.152, and plain windy we have 0.48, which means by going through the values, we can select the outlook, right? But there are other measurements as well, how you may actually calculate this, right? So there are many others because there are various issues with information gain. So to accommodate that one, there's a measurement called gain ratio. So it will modify the information gain and then it will reduce the bias. So it will take number and the size of the branches in the accounting when choosing the attribute, and it corrects the information given gain by talking intrinsic information of a split into a count. Right. So similar to this one, I can show you again another example. We have, for example, we can use, for example, the Gini index, which is again, I'm going to talk about the implementation details. So implementation, the default is Gini value. Very similar to the information gain. You talk about the Gini value before the split and Gini value after the split. The difference will take into consideration. Right. So you can see that with this one, we are going to conclude our session. We mean the theory. Let me talk about the practicals yet. So we will use what we have discussed is called ID3 algorithm, mainly focusing on, in our case, categorical value, and many other attribute selection criteria. We have information gain, gain ratio, Gini index, chi-square, and so on. So there are many ways. So with that, we'll start the lab session, but let's take a small break. The first part, mining toolkit, and then based on that, and then we are going to continue our discussion. So let's open up WEKA data mining toolkit. Right. Okay. So we have already discussed that how we start. Let's start with the Explorer. And under this one, I'm going to open a file. There are plenty of data sets available here you can actually work on. So the first thing that I'm going to discuss is, let's go to C, program files. Let's see 3.8.4 data folder. And there are many others. So let me select first the nominal, right? What do you mean by nominal data set? If you remember, if you click on edit here, you can notice that our data set, we have 14 instances and this is the distribution. So having said that, now to make a classification, you can go to classification tab and you choose the trees, and then we can select ID3, for example. And then if you just say start, you will get some other numbers which we will discuss later on, but you will get this part. This is the textual representation of the tree we have seen. So let me say we have visualization. You can right click on it. We can right click on and we can say visualize free. This is disabled, and the reason is ID3 normally we couldn't visualize. But let's change this from ID3 to J48, which is another decision tree structure. So if you do that, you get the outcome. And when you right click it, visualize free, and here is the outcome. So the outcome actually from the basics that you have used, and also it uses the information gain. In this particular case, Outlook has the highest information gain, and given the others, we have humidity and VT. So you can actually make some trial and error. For example, if I choose, right, base, let's see, multinomial, whether we can work on, yes. And here is the outcome, right? So we were discussing about creating a decision tree in WEKA. So the dataset that we have used is weather dataset, and under the classification, we can select tree structures. So the two tree structures we have discussed, the first one ID3, which will not get any visualization but textual form. But if you want to get the visualization, then we can go for J48, where you can actually visualize the tree structure. So remember that in this particular case, the tree is based on the data that we have used, right? If you see change the data set, for example, let me go back and open another data set. So let's say we have breast cancer, right? Then let's say I'm going to go to classify, same decision tree structure. Okay, so this is the tree. Let's visualize. So this is how we can say fit to screen. So this is the tree structure that we get from WEKA. So there are a few things we need to understand here. Now, in this particular case, in a tree structure that we will get from here, right? It might contain numerical data as well. But what we have discussed is how to use only the nominal attribute. So let me clarify this and again come back to this place. So having said that, let's go to the note again. The few things that we need to discuss is how do you handle various issues, right? Three things that I would like to discuss, and that's what handled by C44.5. And I told you like our version is J48, my little bit improved version that 4.5. Three things we need to discuss compared to the simple algorithm we have discussed early. We need to handle in the numerical data. We need to handle the missing data, and we need to generalize the model. I will explain those. Right. So what we could do is to handle numeric attributes, we can use again information gain. But this time, when you evaluate in this, right, you look at the best split. So which means we have a split something like this. For example, temperature is less than 45. On the other hand, the opposite of this is temperature is equal or greater than 45. Right. So let's look at this with numerical data. So we can know in this data set, we have outlook, no change, windy, no change, but temperature and humidity we are representing with numbers. So given that situation, what we need to do is we need to split on temperature attribute. So we can, for example, start somewhere. For example, let's say temperature less than 71.5. That means somewhere down here, and we can calculate number of positive and negative. So here 4 yeses and 2 negatives, right? When the temperature less than 71.5. Similarly, if you look at the other part, you will also notice there are 5 yes instances and 3 no instances. So if you want to calculate the information that we have discussed early, branching the temperature variable into this might be tricky. But when you apply the information, 4,2 is one branch and 5,3 is another branch. And then we can calculate using like this, the equation I have given you earlier, and you can find the information. And then you can split points halfway between the values, and then you have to evaluate all possible. Right. The next one that I would like to discuss is how do you use multi-valued attributes. Right now we are talking about the binary, but there could be many others as well. Right. The next one is missing values. If your data is missing, sometimes it happens because sometimes it's not relevant or it's a duplication. So the first task is when you're given when you have missing values, you can take it separately. You can think it as another variable and you can work on it. Or you can ignore all instances, right? So you can remove any data points if it is 0. This is less probable because we all, I think, the supports here. Third one is an interesting one. You are going to split the sentences with missing values into pieces. And then depend on that, it will take multiple branches, right? Then another thing that I would like to discuss is the pruning of decision trees. Pruning means you are simplifying the tree. So that means you are not going to create the whole tree. So two strategies are there. The first one is you build the whole tree and then you remove some of the parts. Second one called pre-pruning, which means you write a code and then you stop from one point, right? So this is called forward pruning, right? Usually the post pruning is preferred, right? Pre-pruning again, idea is based on the statistical significant values, and then the problem in this pre-pruning, it might stop in very early, we call early stopping, right? But then there's an advantage compared to post pruning, it will be much faster. In post pruning, right, you build a tree and then you prune it, and then sometimes there are some issues, subtrees might be there due to the chance effects. True pruning strategies, usually we talk about subtree replacement and subtree raising, right? And there are possible strategies, error estimation, significant testing, and MDL principle. So let's look at some information like how you may simplify this. For example, subtree replacement, where you can actually look at what is available right now. For example, this is the original decision tree. And for example, if you look at only this part, what do you think? This part of the decision tree. And that's what we see here. So this part of the decision tree we have replaced with bad, because you see there are a lot of bad outcomes, which means we can simplify, say this is bad, right? The next one is subtree racings. That means sometimes you can remove intermediate values. For example, in this one, we can remove the branch B, and then you will get the adjusted tree structure, right? So we were discussing about the error estimating, right? And if you look at the software choices, we already discussed about the WEKA C4.5. I will discuss in a separate note, how do you select the scikit-learn, the decision tree classifier, right? So this is the summary of defining top-down induction of decision trees. So you can use various different attribute selection, and then based on you are put to a different classes, right? The next one, I would like to discuss two more algorithms. The first one is what we call instance-based representation, which means we can use in here, the algorithms are something like, so the difference from the previous one with this one is it will not create a model. So simply it will store the instances themselves. So that's why we say the classifier name is instance-based representation. So what happens here? So we will select something called symmetry function, and that function will define what is learned. And this is known as lazy learning because there's no training. But then again, you test and debug. So the instance-based learning algorithms selected the nearest neighbor and k nearest neighbor, right? So when you talk about the distance function, right, we need to find out a similarity. Usually we can talk about the geometrical distance. So if you have only just one attribute, you can take the difference. But if you have several attributes, then you have to use the Euclidean distance, right? And then again, nominal attributes, distance will be set to 1 if you are different, or 0, then they are equal, right? Are all attributes equally important? You never know. Weighting the attributes might be necessary, but it's not what we need. So let's look at some mathematical background for the nearest neighbor algorithm. For example, here you can notice that they have defined something called the distance, where you take the differences of the points and then you get the square root of this. This is known as Euclidean distance, right? So the next one is the previous one, we had to rely on the square root. Let's assume that you don't have that, right? And under that, we can talk about the other matrix as well. For example, city block Again, more generalized version of the decision trees and so on. It's called Minkowski distance, and you can see all the necessary information, but you don't have a fixed value where you use a variable for doing that. And then we'll discuss tomorrow as well